In order to show you how can we derive the canonical circuit model, we can use the buck-boost circuit as an example to derive its canonical circuit model. So in the previous lecture, we have used the simple AC average method to model the buck-boost converter. We have derived its small signal model. Now let me plot it one more time. So for buck-boost topology, if we do not consider the unresistance of the circuit components, we can derive its AC small signal model in such a format. On the input side port, we have the input source, including DC bias and small signal AC. And here is a independent source which reflects the effect of the controlling signal. So I D cap. And here we have a transformer. With coupling points on the same side. This transformer can convert both DC and AC. So we use straight line to denote DC transformation and wave line to denote the AC function. The turns ratio for this is 1 to D. And on the secondary side of this transformer, we have the inductor L. And also we have an independent source which reflects the controlling effect. So Vg minus V over times small signal D. And here we have another effective transformer. The coupling points are inverted. And this can also convert both AC and DC. And on the turns ratio for this transformer equals to D prime to 1. On the secondary side of this transformer, we have another controlling impact, which is I D cap. And we have the filtering capacitor. And the load resistor. So here is C, here is R. This is the output voltage, V plus small signal V cap S. So basically, this is the small signal AC plus DC model for buck-boost topology. Then we can see how can we convert this model into the canonical circuit model. So we can modify based on this. So first step, we look at those two independent sources. By fundamental circuit theory, we can push them to the primary side of its corresponding transformer. For example, this one can be equivalent to here. So I will replot it beneath the top model. So this is equivalent to the primary side. The value of voltage source will be multiplied by 1 over D. So here is the Vg minus V over D cap. the L is unchanged here. And on the primary side of the second transformer, the current source can be pushed to here, right? We just plot another current source and also multiply it. Okay, so since the polarity is inverted, so the current arrow is also inverted here. So this will be going downward. And multiply by the turns ratio here, right? So this will become I d cap divided by d prime. And here is the second transformer. DC plus AC. And also the turns ratio is d prime to 1. Filtering capacitor and load resistor. Output voltage. Here is the inductance L. Based on this model, we can do further changes to it. So here we look at the current source. The ultimate mission is to push it to the primary side. But here we can do some tricks to this. So we can first break this line and connect here to the left-hand side of the inductor. But we want to maintain the node feature here unchanged. So we suppose here is node A. Now we connect this source to node A, but we want to maintain the electric property unchanged. So we should add one source here with the same value as this one, I d cap over d. This current source flows into the ground here. So by doing this trick, you will see that the node function in node A is unchanged. And same as here, right? Although we cut this wire, but we add one here, so the current flowing into the ground is still this current source, meaning that this modification is valid here. So we say that the node function unchanged. And next, we do one more step to change this equivalent circuit. So we look at the L in parallel with the current source, right? So those two components are parallel. So our circuit theory class tells us if we have a current source parallel with an inductor, they can be modeled by a Thevenin equivalent voltage source in series with this inductor. So let me do the Thevenin equivalent. Network to this L parallel with the current source. Then we'll have the modified equivalent circuit. So here is I d cap. This is Vg minus V over d cap. 1 to D transformer. this is the same as this one, I d cap over d prime. So now the parallel of L and the current source is modeled by a voltage source in series with the L. So this voltage source is the Thevenin equivalent, right? So we can see that the voltage source will be S Li over d prime d cap. And this one is unchanged as L. So here is the second transformer inverted with DC AC filter in cap, load resistor R. So they are equivalent, right? And next, we look at this current source. As we mentioned, for canonical circuit model, we always want to have the D terms to the input port, right? So we can modify this one to equivalent to the primary side. So we erase this one. And plot is equivalent circuit on the primary side. So this will be D times I d cap over d prime, which we multiply by the turns ratio for the first transformer, right? And next, we will do the similar thing, right? We found that we have a current source here flowing to the primary side, input side, ground. Can we do the similar thing as this one? The answer is yes. So basically, we cut this wire and connect this terminal to here. As we previously learned that in order to make the node function unchanged, we just need to add this source to here. The value for this source equals to this one. This means that the resulting circuit has the node function in the node B. Unchanged, right? Unchanged. And next, we look at this one, right? So this is the parallel of the voltage source and a current source. If you are familiar with the circuit theory, you will know that if we have a voltage source parallel with a current source, the voltage source will dominate, meaning that we can just erase this current source. So this current source has the value equals to d cap over d prime. So next, we can further simplify the model. Basically, we can see that we have two current sources. They are in parallel, so they can be added, right? And moreover, we have a voltage source on the second side of the first transformer. This can also be pushed to the primary side by multiplying the turns ratio for this transformer. And we can add those two voltage sources together, right? And one more step is the L. The L can be pushed to the secondary side of the second transformer with turns ratio equals to 1 d prime over 1. So the equivalent L on the secondary side will be equals to the L divided by d prime square, right? So next we can plot its resulting equivalent circuit. So here is Vg plus small signal Vg. Those two sources are combined into one. So by combining those two together, right, we can see that this will be equals to d prime plus d equals to 1, right? So they are combined to be unity. So here will be simplified as d cap over d prime. And for this source, it is the combination of this one plus this source equivalent to primary side. So the value for this source will be equals to this quantity plus this equivalent. We extract the d cap items. So here will be minus s li over d prime times d cap. And here is the second transformer. The turns ratio is d prime to 1. D prime to d, right? So basically, you will see that if we move this one to the primary side and move this one to the secondary side, then those two transformers, they are in cascaded, right? Two cascaded transformers will be equals to the product of their turns ratio. So this will be d prime over d, meaning that we combine those two transformers together, right? And this is a DC coupled AC transformer. Turns ratio are inverted, right? Here is same, here is inverted. Together is inverted. And on the secondary side, we have the equivalent L, right? As I mentioned earlier, if we push L to the secondary side, the effective L will be equals to L over turns ratio square, right? And C is kept as it is. And the load resistor is as it is. Here is the output voltage. So now, if we look at this one, we can equal the bracket part as ES, right? The coefficient we denote as ES. So ES will be equals to this minus this, Vg minus V over D minus S Li over D prime D. And this one can be further simplified because for buck boost converter, we know that the output voltage over input voltage equals to D over D prime. So basically, we can cancel out the input voltage term to leaving only the output voltage and the duty cycle term. So this will be equal to output voltage over D square times 1 minus S times DL over D prime square load resistor. So that is the ES term. So now let's look at the resulting circuit model. This one is exactly the canonical circuit model we learned in the previous subsection, right? So we can see that its fundamental features, we have the controlling terms existing on the input port side by two sources. One is the input current source. One is a voltage source, right? They have their controlling coefficients. And on the right-hand side here, we have a effective low-pass filter network. Effective low-pass filter. The word effective means that the inductor is not the physical inductance. It is a transduced inductance. Okay, so that's how we can derive the canonical circuit model. So as we can see in this subsection, we can, starting from the simple AC equivalent circuit model of the converter to derive its canonical circuit model. And also we can see that the effective low-pass filter, the effective inductance is not equal to the physical value for the inductance. And it is indeed equals to L over D prime square. This means that for different quiescent operating point, we will have different values for the effective inductance. And correspondingly, the transfer function and also input-output impedance will also change with the different quiescent operating points.